If the incline is frictionless, we need to find the maximum height where the block will rise to in terms of the given quantities and appropriate constants. So here we're dealing with conservation of energy because it's frictionless. So we can say that mgh, potential energy, equals 1/2 mv squared, our kinetic energy. Here we're trying to solve for height, so we rearrange it as gh equals 1/2 v squared, where h equals v squared over 2g. Now in part B, we're looking that the incline is rough and has a coefficient of sliding friction mu. Now we need to find the maximum height where the block will rise. Okay, so KE equals WF plus 0. WF is going to equal F friction times D. So F friction is going to equal mu mg cosine theta, where D is going to equal h over sine theta. Now we step that back in, and 1/2 mv squared equals mu mg cosine theta times h over sine theta plus mgh, which will equal 1/2 mv squared, which is equal to mgh times m cotan theta plus 1. So we're using trig identities here. We rearrange the equation and we get h equals v squared over 2g times m times mu times cotine theta plus 1. In part C, we have a thin hoop of mass m now instead of the block, with radius r moving up the incline with v naught initial speed. So it's a similar thing, but now we have a thin hoop. The incline in part C is rough, and the hoop rolls up the incline without slipping, and we need to find maximum height h. Okay, so 1/2 mv squared plus 1/2 iw squared should equal mgh. Now the m's on the left side and right side will cancel out, so you'll have 1/2 v squared plus 1/2 v squared, since the r cancels out, equals gh, where you rearrange it and you get v squared over g equals v squared over g equals gh over g. So v squared over g is going to be equal to h. Now we're evaluating that the incline is frictionless and we need to find the maximum height. So this is simple. This is just 1/2 mv squared equals mgh again, where v squared over 2g equals h, because here it's conservation of energy since it's a frictionless ramp.